Okay, we're in section 90. My name is Ron Bannon. This is the draft version of Webster Wells's Advanced Course in Algebra, which dates back to the early 1900s. I think the book was published in 1904. There'll be contents. That's the contents from Wells's text. There'll be examples that I'll go through, and there'll be exercises that you need to work on. This document is being prepared for the Prison Mathematics Project participants only. It will be published at a later date. If you need to reach out to me and inquire about that or anything else, my email address is Bannon. That's B as in boy, the @ symbol, NNON .us. All right. Now this is something that may have been a part of traditional algebra, but now it's I would say it's delayed till people reach calculus. So what they're going to do over here is they're going to try to find some kind of an expansion of a rational, which involves partial fractions. All right, and I'll go through the detail for you, but the bottom line is, Wells is very sparse on the language. What I want to do is I want to start doing, saying you should read that, try to make some comprehension of what's being given to you. All right, so as I do that, I want to point out one really big form of this entire set of problems is going to be this over here, and I'll write this down for you. You're going to be seeing this a lot. I'm using the letter U for a reason. And what I want to do is I just want to do the long division for you. And this one's really strange, but this is 1 minus U divide into the number 1. And it's written in a convenient way. I'm going to say if you multiply it by 1, what do you get? 1 minus U. Well, that's a match of the leader. What do you do now? Subtract. You get U. So then you put plus U down because you need a match. What do you get? U minus U squared. You're going to subtract. You get U squared. What are you going to do? Plus U squared now. What's going to be U squared minus U cubed? I think you're seeing a pattern. At least I hope you are. This is U cubed. What do you do now? Plus U cubed. I hope you realize that this will go on forever. This will be U cubed minus U4. Then you get U4. So I'm going to say over here, this thing expands to being 1. Whoops, sorry about that. Let me get my eraser out. Let's go backwards. 1 plus U squared plus U cubed plus this goes on forever. All right? This is a very important outcome. All right? This is a very famous series. It's not true for all U. For example, this couldn't be true for 1. But I'll put this over here. We haven't shown this yet. At least I don't remember showing this to you. This will be true when U is between minus 1 and 1 only. All right? Now what I want to do is I want to do the example. Someone says, I don't know how the example could have anything to do with this. It has a lot to do with this. The first thing I notice about this problem over here, I'm going to just simply break it into 2 simpler fractions. And I hope when I do that, my fractions would look like this over here, or at least somewhat like that. All right? So I'll write this down for you. And this would be A. Again, you have experience now with the partial fractions. And B. And the linear factors would be what? Let's take a look at that. It would be 1 minus x. Let's see if this is true, by the way. And 1 plus 3x. Let me see if that's true. You get 1. You get plus 2x. Yeah, it works out beautifully. And then what do you do? Multiply both sides by the LCD. Again, we're getting better. We just had 3 sections on partial fractions. This is going to be 1 plus 7x equals A. 1 plus 3x. And then I get what? I get plus B, 1 minus x. I would pick an easy x value, and for me, I'd say 1. What do you get? 8, right, if I choose 1. On the right side, you get 4a. You may wonder why I chose 1, because the b would disappear, because 1 minus 1 is 0, and 0 times b is nothing. So this says a is 2, all right? I'm going to write that down for you. This would be 2 over 1 minus x. Let's see if we can figure out the b. It shouldn't be that bad. And, to do that, I'm going to pick, I don't know, I guess let's pick 0, all right? X equals 0. What do you get? Well, I'm looking at the right side, and again, I want to remind you, we're looking at this over here to get that. So if I chose x to be 0, what would I get? You get 1 on the left side. On the right side, a is 2. At least I believe it's 2, right? And if x is 0, I'd get 1 here. And then what do you get for the b? You get just plus b, right? And that looks pretty easy for me. It looks like b is minus 1. So I'll write that down for you. Get my eraser out. And me 1 second. That would be minus 1 over 1 plus 3x. All right, so some of those are you done there. As far as partial fractions, you are done. But then I'm going to say to myself is, I hope you remember we talked about this thing over here. Now someone says, why would you need that? You need that because it looks like this one over here. And you may not believe that. It also looks like this one here. So what I want to do is I want to write those down so it looks like that. Right? So let me write one down at a time. So the first one I notice is just simply 2 times 1 over 1 minus x. Right, that's the first one. That's this one right over here. What would this give me? Well, I'm looking at this and realizing it's almost identical, except this has a u and that has an x. What do you get? 2, 1 plus x squared plus x cubed plus dot, dot, dot. That goes on forever. Let's do the other one. And again, I know it's difficult. I'm going to write it down for you. It's minus 1. And what do you get over here? I got to write it so it looks just like this here. It's going to be 1 over 1 minus a minus 3x. All right, I'm seeing that. I hope you're seeing it too. Is it the same thing as this? It sure is. What do we put down now? Let's write this down very carefully. It's going to be minus 1 times 1. Now it's going to be plus the u. What's the u? This is the u. It's minus 3x. Plus the u squared. I'm going to jam it in there. Plus the u cubed. Plus yada, yada, yada. It goes on forever. So what I want to do is I want to kind of write it down so I can get it all together. All right? So I can get it all together. But like I mentioned, this is a major achievement for you if you got this part done. But I need to write it down so it comes all together. And the way I'm going to do that is just kind of look at it and realize that, you know, I got a bunch of things going on here. And they might be very difficult things we're looking at. But I need to be careful about it. All right? So the way I'm going to do that is just look at, you know, maybe term-wise looking at it. And looking at it, you know, I'm going to say, I don't know, looking at this over here, right? I'm just looking at this over here. And I start to realize that it's really not that bad. I mean, it's 2 times the sum 1 plus x squared plus x cubed. And looking at this over here, I'm just going to simplify a little tiny bit, but let me write this down for you. You know, the first one's going to be 2, right? That's not too bad. And then it's going to be 1 plus x squared plus x cubed plus yada, yada, yada. All right? Minus 1. Let's write this down. What do you get? 1 minus 3x plus 9x squared minus 27x cubed plus yada, 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 yada. Right? I'm hoping you're starting to see something here. And what I mean by that is, you know, maybe I should multiply it through for you, but I don't know if that's important. But let me multiply that through for you. You get 2 plus 2x plus 2x squared plus 2x cubed plus, you get the idea, yada, yada, yada. Let's do the next one. What do you get? Well, you're going to get minus 1. I'm going to line these things up that way. Plus 3x minus 9x squared plus 27x cubed. All right? Yada, yada, yada. I'm going to start adding it together. All right? I know it's difficult, but we want to encourage you to add things together if you can. What are you going to go over here? Let's write this down term by term. Again, we're going to write down term by term now. 2 minus 1 is 1. Let's do the next one. But as I do the next one, I'm not going to add it together, although you could. 2 plus 3 is 5. What I'm going to write down is I'm going to write down 2 plus 3x. I'm going to put the next term down. What's it going to be? 2 minus, well, I could write down 9, but I'm going to put down 3 squared because I want to see the pattern. Right? What's the next one going to be? Plus 2. It's always a 2, by the way. And then what I get plus 3 cubed, x. And I think I'm sorry, this is square and cubes. I'm sorry about that. I think I could write the next one down without too much. I know there's a 2 there. And it looks like plus minus 3 to the 4th, x4. I could do this forever, all right? So what I want to do, I'm going to get my little eraser out. And so I want to write the first term down in that pattern over there. See if I can do that, all right? So let me just erase this over here. Whoops, I'm not getting an eraser out. I want to write that first term down. I want things to look the same each time, all right? I know it's difficult, but I'm going to, try to put something down. I'm going to put down, let's see what I got. I have no x's, right? Hope you agree with that. And it looks like it's always going to be a 2, right? And then what would I get? Looking at that, minus, plus. Looks like minus then, right? 3 to what power? Well, 0. Right, what they got is, I get the 1, as I expected. Now, someone's going to say, this is a really interesting pattern here, and it is. This goes on forever, ... And I can write this down. And the way I'm going to write it down is kind of looking at it. I'm definitely seeing x's in the problem, right? So I'm going to put this over here. Like, I got x's. I'm going to use this notation over here. And I'm going to start. Right? So when are we going to start? Well, I'm going to write this down. Again, it might look different in my K. That does okay for me. 0, 1, 2, 3, 4, yada, yada, yada. So I'm going to say, let's take a look. N equals 0, and I'm going off to infinity. Because it just doesn't stop counting. 0, 1, 2, 3, 4, 5. And what goes over here? The power. I'll put this over here. Now I got to put this part down. And this is the tough part. Write it down for you. And again, we'll talk about my answer later. I'm definitely seeing a 2. All right. Now I'm definitely seeing a 3. 3 to what power? Well, it looks like 3 to the n. All right, let me point out that 0, this is a 1, that's a 2. Let me get my highlighter out. 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, so forth and so on. I'm going to say 3 to the n. We'll clean it up later. There's a problem here, though. And what's happening is it's going back and forth between minus and plus, minus and plus, minus and plus. So I got to figure that part out. All right. The way I'm going to do that is I'm going to write down, and again, I have to expand this out a little bit because I'm running out of room. Let me erase this. I'll put that down again. I can remember that. And I think I put down this over here, n equals 0 to infinity. I put down 2. I put down 3 to the n, and then over here I put x to the n down. Hope you remember that. But remember that signs alternate between plus or minus. Well, let me write this down. I'm going to put a plus sign here, but I want to put a minus 1 in front. And how would I get it to alternate back and forth? Well, if you put n to be the first power, right, it would be minus 1. But I notice that I want it to be a positive number at that first power, and I want this to be a negative number. So what I'm going to do is I'm going to put n plus 1 over here. All right, let me keep going with it. See if that works out. If n is 0, what would you get? Yep, it works. I get the first term. If I put n equals 1, what do I get? Well, that would be n plus 1, which is square. That would be plus 1. Yeah, it seems like it's working out pretty fine. I want to keep continuing this up, by the way. But by the way, this is an answer. This is a fine answer. All right? I want to clean it up. Someone says, why do you want to clean it up? I want to see what it looks like. All right, so let's put this over here. It's going to be the sum. N equals 0 to infinity. Okay, the first thing I want to do is I want to do this minus 1 to the n plus 1 times 3 to the n. That's going to be minus 1 to the first power minus 3 to the n. All right, now someone said, what'd you do over there? I kind of looked at it, and I kind of divided that minus 1 to n plus 1 into two different factors, minus 1 to the first power and minus 1 to the n. And then just combine them together. That's all I've done. So let's take a look at that. What does that give me? That would give me minus 3 to the nth power. Let me write that down for you now. That would be 2 minus 3 to the n, and we'll check it out, by the way, times x to the n. Now, when I say I'm checking it out by putting numbers in. So if you put n equals 0, what would you get? I want to make sure you know what I'm doing over here. I'm checking. If you put n equals 0, you'd get 2 minus, well, minus 3 to the 0 is just like 3 to 0. It's 1. That's going to work out beautifully. Let's see if we get the next one. And I'm going to the number 1 now, right? So what do you get? 2 minus a minus 3, which is 2 plus 3. I'm seeing that. Let's do the next one. What's the next one going to be? 2 minus, well, minus 3 squared is the same thing as 3 squared. Yeah, it seems like it's working out beautifully, so forth and so on. So it's a good-looking answer. Could you write it differently? Of course you could. So over here, you notice I wrote them a little bit differently, right? A little bit differently. Is it the same thing? It's the same exact thing. So this is a good answer, and that's a good answer. But they're the same answer, and you may want to do that by expanding them. Okay, this is something that Wells doesn't do, and I'll tell you why he doesn't do it. Graphing was very difficult back then. But what I do here is I graph out a partial graph of the function, this guy over here. I want to point out what that is. Looking at the picture, the function looks like this over here. All right, that function's defined everywhere except at where the denominator becomes 0. Let me go back over that. Where's the denominator become 0? Well, looking at it at 1 and at minus 1/3. So what do we know about this over here? At 1, let me put this down for you. At 1, there's going to be an asymptotic behavior. And at minus 1/3, there's asymptotic behavior. All right? What does that mean? This graph will look like this over here. And this graph, it goes towards that, and it goes toward it over here. The other thing I graphed out was, I graphed out the 5th degree expansion. So what expansion are you talking about? This one over here. So what I do is I took this thing, and I simply expanded to 5. So let me point out what I mean by that. I did this. N equals 0 to 5 of this. 2 minus 3 to the n, x to the n. Let me go through that with you. All right, what's the first term going to be? Well, if you plug in 0, what would you get? You get 2 minus 1, which is 1. X to the 0 is 1. What do you get for the next term? I got to be careful here. So the next one's going to be, let's see, I do 1, right? So what do you get? You would get 2 minus a minus 3, which is 5. X to the first power. I'm going to do the next one. The next one is I just did 0, I did 1. Now I'm going to do 2. What are you going to get? 2 minus 9. That's minus 7. X squared. All right, let me keep going. And this is why Wells wouldn't do this. He's become incredibly difficult to graph out in Wells's error. I mean, really difficult to graph out. They may have known what it looked like, but they'd have a very difficult time constructing an accurate graph of this. I have a machine that does that. So we did 0, 1, and 2. Now we're going to do 3. What are you going to get for 3? Well, let's see what you get for 3. That would give you 2 plus 27, which is 29, x cubed. Now I'm going to go to 4. What are you going to get? Let's see, 2 minus 81, which is going to be minus 79. x4. I'm going to get a 5 now. What are you going to get? Well, if you did 5, you get, let's see, 243 plus 2, 245. I'm just doing the arithmetic. x5. I'm going to stop there. Why is that? I want to do a 5th degree approximation. The 5th degree approximation is this curve over here. And it looks just like the other one in a region. What's the region? It looks like it's, at least with the 5th degree thing, it looks like it's fitting between certain numbers over here. And believe it or not, no matter how far you take this out, it would never fit it beyond what we say it would fit. And the fit would only occur between those two numbers over there. It's an impeccably good fit the further you go out. Now, I do want to point out over here, the fit is certainly better on this side than it is on this side at this point. We're at the 5th degree. All right? So that problem's done. What's the big deal about this one over here? It is tough. I'm not saying it's going to be easy for you. First thing is partial fractions. Next thing is you're looking for this pattern over here. Are there other patterns to look for? Yes. If you have a tough time with the summation notation, you know what? You can skip that for the time being. But this is something. This is going to be our goal. If we can get there. I'm not saying you're there yet. If you can get here, consider yourself a champion in this. If you can get here, you really you're controlling the entire world in this. All right? Let's see the next one, if there is a next one. Oh, Wells doesn't give many examples, does he? So what does he talk about now? He talks about your ability now thinking that you can do the exercises. I know this is going to be tough. So what does it say? Find the nth term expression of this guy over here. Again, I can't say it enough times, you got to get the partial fractions down. All right? Now, what I would do over here is saying I need to remember certain things. Let me point out what I need to remember. I need to remember this one fact. Sorry about that. This one fact I need to remember, sorry about that, I'm going to erase that. I need to remember that this here is very simple. This is with the understanding that u is between -1 and 1. And what do I see over here? I see 1 plus x. Your first thing to do is write this down. 1 over 1 minus x. So what's u? It's actually minus x. So what would this expand to? 1 minus x plus x squared minus x cubed plus x4. I think you get the idea. Minus x5. And it goes on forever. All right? So that's all I did over there. What's the other one going to be? Well, the other partial fraction is going to be this one over here. 1 over 1 minus 2x. What's the u here? It's actually 2x. We're going to get 1 plus 2x plus 2x quantity squared plus 2x to the third plus yada, yada, yada. And that stuff is written over here, all right? By the way, I also write down the nth term, but right over here, I'm writing this stuff down over here. Oh, you know what? I didn't realize there's a 2 on top. I'll put that down later, by the way. I didn't do that. But you could multiply it by 2. Let me put that down for you. So 2 over 1 minus 2x is going to be 2 times what's above it. And write that down. 1 plus 2x plus 2x quantity squared plus 2x cubed plus yada, yada, yada. All right? If you multiply that out, sorry about that, I didn't put the equal sign over there. If you multiply, what do you get? 2 plus 2 squared x plus 2 cubed x squared plus 2 4x 3. All right? That's why I'm writing these patterns over here for you. All right? There is a pattern to it. Now, again, I realize writing these things down, what the nth term is, it's tough. All right? You got to get the pattern for it. And I realize that's difficult. You want to kind of aim for that if you can. Right? Also, the summation notation, I realize it's new, but you also may want to write the summation down. This one over here, really the same story. What are you doing? Breaking it up using partial fractions. What should you notice over here? Well, the first one's going to be 2 over 1 minus 4x. What does that mean? Well, I know what the u is. It's 2 times 1 plus 4x plus 4x quantity squared plus yada, yada. Again, let me repeat this. We're looking at this pattern over here. It's a very simple pattern. We did that by long division, by the way. What's the other one going to be? Well, minus 3 over 1 minus 5x. That's going to be minus 3 times 1 plus 5x plus 5x squared plus yada, yada, yada. It goes on forever. That's what we're doing in this thing over here, writing them down. It takes time, though. What takes time? Seeing the pattern, partial fractions, and writing down the ultimate pattern, which is actually the nth term. That's what we're writing down. You can always check that by looking at the key, or more importantly, looking at your work and make sure it matches the nth term in your work. Same thing. Right? Partial fractions. Same thing. Partial fractions. Okay, this one looks more difficult to me. I'll tell you why. I'm looking at this one over here, and I'm definitely seeing the pattern. But over here, this looks more difficult for me. All right? So what did I do over there? I kind of broke it into 2 different parts over here. It's still the same pattern. Someone says, I don't understand how that could be the same pattern. Let me just do one of them. Let me do this one over here. It's going to be 2 times 1, and I got a 3 here. I don't want a 3. And I'll tell you why I don't want a 3. This is supposed to be 1 over 1 minus u. What is this equal to? 1 plus u squared plus yada, yada, yada. Well, I got trouble. There's a 3 there. I'm going to factor it out. What do you get? 1 minus 2/3 x squared. What do you get over here? 2/3. I know it's tough. It's going to be, let's see, 1 plus u. This looks just like this. What's u? It's 2x squared over 3. All right, what's the next one going to be? Plus 2x squared over 3 squared. Yada, yada, yada. It goes on forever, all right? So maybe I should do the other one too for you. What's going to be? Well, I'm seeing it. I'll pull the x out. And what do I see? I see 1. I see the 3. I don't want that. I want it to be a 1 in the bottom. I pull the 3 out. And what do you get over there? 1 minus, you get this? 2/3 x squared. We're always aiming for that, by the way. What do you get over here? X over 3. 1 plus 2x squared over 3 plus 2x squared over 3 quantity squared plus it goes on forever. All right, what's the big deal about this one over here? Yeah, it's a lot of work. What's the work going to be? I got to be honest with you. It's getting this thing over here. It's a lot of work. The other expansions really aren't so bad. It's the work. Also, the interval of convergence, it's also going to be work. But right now, let's not worry about that. Let's just see if you can match these nth terms. And I know it's difficult. Another example of a tough problem. What's tough about this one over here? Well, this one looks really obvious to me, but this one may not look obvious to you. What's going to be? Minus 5, 1 over 1 minus, let's write this down, minus x squared. All right, if you write this down, what is that? Well, it looks like the pattern I'm expecting. What's that pattern? The pattern's this one over here. It looks just like it. What does this look like? 1 plus u squared, da 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 da. Let's put this down. Minus 5. What do you get? 1 plus, well, what's the u? It's minus x squared. Plus minus x squared plus yada, yada, yada. Again, this stuff is written down for you. We want you to look at that, and we want you to see if you can get the pattern. The pattern can be tough. This needs practice. What do I mean by practice? Looking over what we've done to get those terms. What's the ultimate goal in the terms? If you know the terms, you can write the sum down really quickly. All right? That's what we did in the first one. I realize it's a very tough section. It is, no doubt about it. Here's the deal. Go to Sage. All right, you're gonna see something remarkable about Sage. Whoops, sorry about that. I keep doing that. So Sage, what's Sage? It's a computer algebra system, or a CAS. It's free. What does that mean? It's open source. This is the website. You go there. You either download the application or interactive web-based application, any one. Go through the code. All right, what are we doing with the code? Partial fractions. Why do we do that? We've done that in the past. Then they got this word down, Taylor. You should look at that command. And what Taylor does, it writes down the series for you. Now, part of the series. What series over here? This one here, I'll circle it for you. This would give the 5th degree, right there. Now, you may want to look back in your notes and see how remarkable that is. All right, now Taylor series is being taught at this period of time. They didn't mention Taylor, by the way. It's being taught this period of time back in 1904. Now, by the way, it can be done in algebra. This can be still done in algebra. We're doing them in algebra. But the reason now is we've lost contact with this type of algebra. So this stuff here is delayed until we get to calculus. But here's the deal. You should realize you don't need calculus to do these series problems. They're super simple. Now, when I teach calculus, and it does vary a great deal, I often tell students that a lot of the stuff that we're doing is just algebra. It doesn't require knowledge of calculus, and it really doesn't. It's just algebra. And this is some of the lost stuff that we have in algebra, that a lot of this stuff that you're being taught in calculus, when you get there, they're telling you, oh, you need calculus. You don't need calculus. You need algebra skills to do the problem, all right? Again, if you need to reach out to me by pointing out errors, whatever, for whatever reason, my name is Bannon. My email address is Bannon, that's B as in boy, the @ symbol, NNON.US. Again, I really appreciate students that reach out to me to let me know there's errors. And if there are errors, I'll correct them. It's really that simple. Thank you for paying attention.